Polarity. These two pictures are pretty awesome at showing what polarity is. If you look at the one on the left, we have chlorine and hydrogen sharing their electrons. But if you notice, chlorine is pulling them a lot harder. It's got like this evil looking face, and hydrogen is trying to hold on tight. And this would represent a polar covalent bond, whereas the one on the right, both the hydrogens are happy sharing their electrons. This would be a non-polar covalent bond. Okay, so notice, like I said, that the chlorine was pulling on extra tight. Hydrogen looks like it's trying to hold on for dear life. That's kind of along what polarity would be. It describes the unequal sharing of electrons in covalent bonds, and of course it's dependent on electronegativity. So if you remember, electronegativity is the tendency for atoms in a covalent bond to pull the electrons tighter, and it is dependent on the size of the atom as well as the nuclear charge of the atom. So looking at a periodic table, the electronegativity trend increases as you go up because the smaller the atom, the less the distance is between the nucleus and those electrons, so it feels a greater Coulombic attraction, so it will hold on to those electrons tighter. Electronegativity also increases from left to right across the period because as you go from left to right, while the size barely changes, what does change is the nuclear charge. There's going to be more protons in fluorine compared to that of oxygen, and therefore it will have a stronger Coulombic attraction, or stronger nuclear charge. It'll be able to pull those electrons in tighter. Of course, we're negating the noble gases because generally they don't form covalent bonds and so won't have an electronegativity, generally. If we look at hydrogen monofluoride or hydrofluoric acid or hydrogen fluoride, whatever you want to call it, we know that fluorine is the most electronegative atom on the periodic table, or most electronegative element on the periodic table. Okay, so those two electrons that it's sharing with hydrogen is actually going to be a lot closer to fluorine than it is to hydrogen. When that happens, fluorine obtains this partially negative charge. This little symbol here, I don't remember what the letter is, but it indicates that this is a partial negative charge. It's not full on negative because it's not completely taking the electron from hydrogen, but it is holding those electrons closer, so it will be partially negative. If it's partially negative, that makes hydrogen partially positive. Okay, when this occurs, we call this a dipole moment. This would indicate that we have a polar bond, which we call a dipole moment. So if you're looking at which bonds would be more polar, we have to look at the differences in electronegativities. Boron to chlorine or carbon to chlorine. Carbon is closer on the periodic table to chlorine than boron is, therefore its electronegativity is probably more similar to chlorine than boron's is, which means the difference in electronegativities between boron and chlorine is greater, which means that would be a more polar bond. If you want to pause the video so you can see if you can figure out the next example, go ahead and do so now. You do it similarly. Phosphorus to fluorine or phosphorus to chlorine. Fluorine, again, is the most electronegative element on the periodic table, and phosphorus is closer to chlorine than it is to fluorine, so that makes the difference in electronegativities greater between phosphorus and fluorine, which means it would be most polar. Now, molecules can have polar bonds, but they might not be a polar molecule. So they might have those dipole moments, but they won't actually be a polar molecule. There won't be an overall partial negative or partial positive charge. And the reason that is because those dipole moments are vectors. If you remember from physics, vectors have direction and magnitude. So if we look at carbon dioxide here, oxygen we know is more electronegative than carbon. Both oxygens are. So the dipole moments are going to be pointing towards oxygen. Oxygen is going to be partially negative, oxygen is going to be partially negative. This arrow with the little plus sign at the end indicates the direction of the pull of electrons. So it's like a partially negative here for carbon, partially positive here for carbon, partially positive here for carbon. But if you notice, they're equal and opposite because they're both oxygens. So equal and opposite, just like vectors in physics, they're going to cancel out. So while there are these dipole moments within the molecule, overall, carbon dioxide is considered non-polar. So if we look at two more examples, water and boron trifluoride, we have to look at their electron domain geometry, but more closely at their molecular geometry. So this would be an example of a drawing of the Lewis dot structure for water. And it looks similar to carbon dioxide in that they're both aligned, they're both hydrogens. But what we have to remember is that water is actually bent. Okay, we have those lone pairs up here that are bending those hydrogen atoms down. And we know oxygen has more electronegativity than hydrogen, so it's going to hold those electrons in tighter. Okay? So I'm going to move these vectors to the side here so it's a little bit easier to see. And if you remember, again from physics, when we do vector addition, we go head to tail on the vectors. Okay? And as we can see, those vectors do not cancel out. So therefore, water is a polar molecule. In fact, it's probably the most famous polar molecule, and it's one of the reasons water is the most amazing substance in the world is because of its polarity. The second example was boron trifluoride. This is the Lewis dot structure of boron trifluoride. If you remember from previous lessons, boron is one of those few elements that can have less than an octet and be considered stable because it's not electronegative enough to force fluorine to share an extra set of electrons, especially because fluorine is so electronegative. So if we look at this, remember that this one is actually trigonal planar. So all those fluorine atoms there are all on the same plane. And again, fluorine is more electronegative, so it's going to be holding on to those electrons, and we get those dipole moments in each of those bonds. So each of these bonds is a polar bond. But is the molecule as a whole polar? Let's check it out by looking at the vectors. 1, 2, and 3. All three of those vectors will cancel out, meaning boron trifluoride will be a nonpolar molecule. The reason this works is because this is a symmetrical molecule. All the atoms are the same, all the angles are the same, so it will all balance out. Here's some practice problems for you. It says, which of the following bonds is most polar? Feel free to pause the video. If you remember, we check the electronegativities. Which one will have the greatest difference in electronegativities? That will be most polar. In this case, it's going to be that one. Number 2, is the molecule polar as a whole? CH4, also known as methane, is tetrahedral shape. All hydrogen atoms bonded to carbon. All the bond angles are the same. All the dipole moments are the same. Therefore, all those vectors are going to cancel out. Methane is non-polar. Ammonia, which is nitrogen trihydride, is pyramidal shaped. It has that lone pair of electrons on nitrogen. Because of that, this is an asymmetrical molecule. Not everything is going to balance out. Not everything is going to cancel out. So ammonia is a polar molecule.